This is the 5th video in the series Physics Fundamentals. In the first two I spoke about the structure of bodies of mass being in molecules and atoms, and then in nuclei, which consist of protons, neutrons and electrons. And then we spoke about Einstein's special theory of relativity, in which we described how the mass of a body increases with the velocity. And I've put a table on the website, fatherphysics.com, showing how the energy varies with and without Einstein's special theory. And this is the graph that I've drawn showing what's on that chart, that if as the velocity of a body increases, then without Einstein's theory, the energy increases as the mass of the velocity, half the mass times the velocity squared. That's the energy given to a body when it's accelerated, and it's called then the kinetic energy, because it appears to stay with the body as long as it's moving. And as you see, this line here shows that when the velocity is 0, the body has no kinetic energy, and as the velocity increases, the energy increases also. This line will never reach vertical, because no matter how high the velocity goes, the energy will increase with it, with increasing rapidity. But Einstein showed that if you put here the speed of light at c, which of course is very high compared with any velocities that we normally encounter, when you get to c, you cannot go any faster. And therefore he showed that this line is modified to an equation which says that the kinetic energy is equal to c squared times the mass increased, the rest mass taken away from the relativistic mass shows the increase in mass. And so this curve, when you plot that now, as I've shown in my spreadsheet that's on the website, this starts off when the velocity is low. This equation, if you expand it, and we did that on the 4th video. If you expand that, you see that as the velocity increases, whilst this curve now starts at the same way, it levels off and never reaches c, or at least not until the energy is virtually infinite. And so that is quite a remarkable change in mass. And so what I'm going to talk about now is, what is mass? Because we've always thought of mass, and still do in many ways, think of mass as the amount of matter in a body of mass, so that the Earth has a certain amount of mass. But the thing is, though, that if the mass increases relative to a certain observer, because the Earth is moving relative to that observer, if you look at another solar system, for example, the Earth may be moving very rapidly, then does the amount of matter increase? And the answer to that is, that's quite impossible, because with the different observers you could have throughout the universe, the Earth could be moving at all kinds of different velocities, and therefore would have all kinds of different masses. And because of the energy being different between the Earth and other bodies. So can the Earth therefore have different amounts of matter? Well, that's not possible if we define matter as the number of units of matter that are in a body such as the Earth. You'd have to increase the number of protons and neutrons, or make each of the protons and neutrons more massive, and it would be different for different observers, and that's really quite impossible. So we really can't think of mass anymore as being the amount of matter. It does depend on the amount of matter, but it's a property of the Earth, so it appears, and that causes the Earth to resist acceleration. so that when the sun attracts the Earth by gravity, the Earth reacts according to its mass, and that will depend on its velocity in the frame of reference in which an observer is on the sun. So I'm going to now then talk about what is mass if it's not the amount of matter. First of all, I'm sure you know that there are different kinds of variables that represent quantities, and some of these are said to be absolute and some are said to be relative. And the velocity, everybody knows, is a relative variable because the velocity of something depends on what the observer is doing. If the observer in one car is passing another car, then the relative velocities are different from the speed of the cars relative to someone who's standing on the sidewalk, such as a policeman with a radar equipment. So velocity is a relative variable. Well, so is mass, because as you saw from Einstein's equation, the mass varies according to the velocity. So what therefore is mass? Well, it's rather interesting. If we look at the definitions of mass, we could say that it was Isaac Newton who defined mass by saying that force is mass times acceleration. This type of equation is very typical. Distance equals speed times time, for example. Energy is force times distance, and so on. That type of equation is an indication that somebody at some time defined one of these variables from the other two, so that we could say that force, for example, can be defined as the mass times the acceleration. But you could also say that mass is defined as the rate of change of force as the acceleration changes. And that's written like this, that the mass would be, I'll do it with a color you can see, that the mass is equal to the rate of change of force divided by the rate of change of the acceleration. That's called a differential equation. And this is the slope of mass as it varies according to the acceleration. It's the acceleration that causes the mass to change, and the acceleration is considered usually to be caused by a force. Actually, later on in later videos, I'll be explaining that acceleration is not really caused by force, but the force is an effect that, or a symptom which, or something that we use as an excuse for acceleration. But the acceleration, if it occurs for some other reason, can give the perception that you've got a force. So this makes definitions a little difficult. In terms of Einstein's theory, mass can be defined as the rate at which momentum changes as the velocity changes. So it's really an effect. And in a later video, the next one, I'm going to explain how these all relate to one another, particularly as regards energy is concerned. I'm going to talk about energy dimensions, because if mass is not the property of a body, what is it the property of? Well, it's more the relationship, the property of the relationship between two bodies. So that where the moon, for example, has a mass that depends on its relationship with the Earth, and so mass is more a property of two bodies, and we'll talk about that in a later video. But thank you for watching this one. Thank you. Bye bye.